First speaker today is Mike Mazarek. He is the program director at Geosystems Analysis. He has been doing aquifer recharge work for, 30 years? Is that a good number? Almost, okay, almost 30. Has done work, I know, on 2 continents, maybe more than 2, at least 2 continents, and in a good part of the western United States. He is also a consultant that I've worked with in the past and currently working with at my district, Rolling Plains. The other thing I know about Mike is he hires some of the most intelligent people on earth. If you want to see a good, healthy company resume, look at his staff bios. They're great, great. Okay, if y'all could welcome Mike.
Thanks, Lynn, for your kind introduction. I'd like to thank the Texas Groundwater Summit and Rolling Plains GCD for inviting me here to give this talk. My title doesn't exactly reflect my talk, but that's all right. But I'm going to spend some time going and overviewing the different types of MAR, some of the constraints in Texas, and then discuss a methodology which really applies to any type of MAR that you do, whether you do aquifer recharge or ASR, and try to give you guys an idea of what some of the opportunities might be. So there's a lot of different types of MARs. Most of you folks know about spreading basins. There's what we call riverbed filtration. This is induced recharge. I'll talk about that in a minute. A recent development is what we call AgMAR, flood MAR, or on-farm recharge, and that's basically where you're taking high flood flows, excess water during the periods of time you have it, and you're applying it and you're putting excess irrigation on. It could be fallow fields, or it could be actually, they do a lot with orchards like grapes and pecans, for example. I'm going to discuss stormwater capture and recharge. And that's actually going to be the focus of this talk mostly is stormwater capture and recharge. And then I'll go over recharge enhancement methods, and then I'll touch on direct injection, but Neil Deeds from Intera is going to give you a much better insight into that than I can. So surface spreading basins, that's pretty obvious. You basically dig a hole, excavate it. You don't want it too deep, but it needs to be in a type of sediment that's quite permeable and that is in connection with groundwater, okay? And so there are limitations. Not every place is good for surface spreading basins. If you get a low recharge rate, typically below 6 inches per day, that's actually gonna lead to a lot of evaporation in the summertime, so it's not, those aren't great basins. These are just some examples of what some basins, like in Arizona and California, and you can see a lot of these are basically old ag fields that are in highly permeable sands. The growers actually kind of know which fields take a lot of water, and then you can convert that into recharge basins. AgMAR, flood MAR, I kind of touched on that already. It's getting a lot of traction. They're doing probably a couple million acre feet per year in California at this time, and they're applying a lot of water. I wouldn't say it's highly efficient yet. Everybody is just on the bandwagon because they want to get as much water into the ground. What's also interesting is that if you have irrigation ditches, you have a lot of losses in irrigation ditches, or you can. And for example, I was working in Montana recently, and kind of the rough estimate is they're getting about 2 million acre feet of recharge from their irrigation ditches, which are primarily coming off of the rivers and going into the very permeable sediments where they're growing mostly on the western side of the state. You can do it into ag fields. There's a lot of research on that. It can't be done. You can't do it continuously. For example, you can't flood your orchard for 3 months, but you can do it for 2 weeks, and then let it rest, give the oxygen to the roots, and then come back again and do it again. So lots of work on that. Riverbed filtration. The reason I bring this up is it's not traditionally looked at as a MAR type operation, but it really is, because what you're doing is you're creating a gradient from the river by lowering the water table. If you've got and these have to be wells that are in connection with the river system, and you're causing recharge. And the perfect example is Texas and New Mexico are in a lawsuit because New Mexico, south of Elephant Butte, pumps heavily off the Rio Grande, or in the alluvial system off the Rio Grande, so that the water that's released to Elephant Butte doesn't all make it to El Paso. And we'll let the courts figure that one out. But the other thing I would add is that riverbank filtration is heavily used, for example, in Europe as a water pretreatment, because that process of infiltrating water through the sediments removes your pathogens. It also removes your sediments. So there's many countries in Europe that do not allow chlorination, for example, and they're able to do this because they're pulling water from induced recharge, and then they can go with lighter disinfection methods. This is an example of increasing recharge in surface water channels. This is just a very simple structure. It's a low-grade crossing underneath a bridge, and they just elevated it. This is in Pima County, and what that does is that causes the water to back up on this side. So you get more spreading water out, you get a higher head, more recharge. Very simple. And then you can see the downstream down here. This is another example of this is for areas that have more or less permanent flow. You're basically trying to slow the water down, spread it out, increase the amount of retention time, increase the head. You can take old oxbows. I've seen people do that, or put in small diversions. This is an example of just putting in small check dams, and you put enough of these in your system, and you can double, triple the amount of recharge that's naturally occurring in a stream. This is an area of Orange County Water District on the Santa Ana River, and they have a bunch of recharge facilities, but what they also do is they push up sediments, which is very sandy material, and they have what they call T&L levees, and all this does is slow the water down, causes it to back up. Again, they increase their recharge. I don't remember the numbers, but they're getting probably 50,000 acre-feet per year through this scheme in recharge just on water in the Santa Ana River. So you don't always have nice, perfect sediments at the surface. At that point, you have to start looking at recharge enhancement methods. A couple of very common ones are dry wells and infiltration galleries. Dry wells are very common in the western United States, for example. In the Phoenix Valley, there's over 50,000 dry wells that have been drilled into typically detention basins in urban areas. It's basically a large diameter, typically 4 feet diameter borehole, and you might have a centralized, a slotted PVC pipe down the middle, and then it's backfilled with gravel. You can get down to about 125 feet below ground surface. You do have to design, you have to put some type of sediment removal, whether you put sand at the surface or you have a sedimentation chamber. You have to control sediment flow into the dry well, otherwise you're going to ruin it because you'll clog it up. And then it has to be maintained. Typically, at least once a year, you got to get in there and muck out the sediment. And it's also a Class 5 UIC well, so you do have to get it permitted. Arizona has primacy. It depends on your state as to what's going to happen. Infiltration galleries are just basically much bigger dry wells, but they're at the surface, and you're doing it with an excavator. So typically, you're limited to 10 to 15 feet. So if you've got clean sands underneath a clay layer, an infiltration gallery is a way to bypass that limitation. Filter fabric sand layers at the surface, again, that can be cleaned. But again, the designs, you have to be careful. You have to make sure it's big enough aerially so that it doesn't get classified as a Class 5 well. Here's an example. This is where you're getting into very high costs, but parking lots, parks, these pictures are out of Southern California where you're diverting water, surface water runoff from streets. It's going underneath the parking lot into this structure, which is actually built to handle a load, and then it's infiltrating. Now, the maintenance on these, it could be tricky, but it's a high dollar for urban environments. Another recharge enhancement method is that's gotten been come through in the last 5-6 years is reverse tile drains. So this is basically a tile drain that you would use to lower groundwater, except now you're putting water in, so you have to have a water table that's 20, 30 feet down. This is a trencher, and it's a one pass, and this typically gets down operation to about 15 feet. There's a pipe, slotted HDPE pipe that goes in, and there's backfill with gravel, and then they push everything over the top. Well, at that point, you can then, you've got a vault, you put water in the vault, and it sends it onto the pipe, and you recharge it. And so there's at least 20 of these systems that have been installed in California over the last 2 years. And it's could be used for parking lots, it could be used below orchards, ag fields. It's getting a lot of interest, and particularly because you can backwash and you can clean these suckers out. Now, that said, you have to have clean water to put in, so you have to have some type of filtration system that you run any water through these. Other recharge enhancement methods are Vados injection wells or gravity drainage wells. This is, I would call it intermediate between a dry well and an ASR. It's plumbed, it's under pressure for Vados injection, and that's an example. So it's very similar. The disadvantage to Vados injection wells, even though they're cheaper, they're a lot cheaper than ASR, is that they're very difficult to clean. So if they clog, you might end up having to drill a new one. Gravity drainage wells are just a much simpler design, and you're simply putting water in through gravity. But again, this is more controlled. You're going to have to keep, the water's going to have to be cleaner if you're going to be using this type of a system. And then ASR wells, I'll let Neil explain this slide. But I did want to point out that with these recharge enhancement methods, if you can't get in the surface, the cost, the relative cost in terms of both capital and O&M goes in this direction. You know, infiltration galleries are quite simple, dry wells, Vados injection wells until you finally add ASR. Okay, so I'm going to spend the rest of the time talking about stormwater capture and recharge, and mainly because it's difficult to build reservoirs anymore. So, and a lot of water's already been used. So this is kind of really the area where we need to figure out what the opportunities are, how much additional water can we get. So a lot of this especially is pertinent for urban areas because you've changed the hydrograph, you've got flooding problems. You can, the question is, can you capture enough of those flood flows, those higher peak flows, and put it into the ground? Some of the questions is, how can you capture it? How do you improve the water quality? And of course, the site suitability. And then the last thing, of course, you have to look at is water rights, in-stream flow requirements, and I'll touch on that in a second. So how much runoff and when? There's really two things that have to go on here simultaneously. Number one is you have to start looking at the hydrogeology. You look at the watersheds where you're trying to capture water, and at the same time you have to do a full-blown surface water analysis because there's no sense in spending a bunch of money on a recharge facility if you don't get a whole lot of water going there, right? So you need to balance those two things out. So in terms of precipitation analysis, we always shoot for the longest record. Typically, you get that from NOAA. Mesonet's good, but there's not much before 2000. So you may have to go deeper. If you don't have data, you can use what's called PRISM. And then what we like to do is we classify each of the years into wet, dry, and average, and I'll talk about that in a second. Watershed analysis, pretty straightforward. You want to define where you can get your potential stormwater capture points, and then, of course, go through just the surface water analysis. It can be very simple. It could be just a SCS curve number, or if you've got a HEC-RAS model for the area, that would be better. So then in with the stormwater runoff analysis, what we like to do is select representative years at the frequency of occurrence. And what that means is that there's a lot of variability in precipitation, right? So if you just pick 1 year or a design storm event, you really don't know how much water is going to go to your capture point. You don't have a good idea over time. So once you pick these representative years. You then model all the individual precip events from that year, and then evaluate what can be captured. And then I'll talk a little bit about urban enhanced runoff and non-adjudicated water. So this is a graph. So we have years on the x-axis, and then precipitation on the y-axis. We're looking at El Paso, Amarillo, Austin, and Houston. And obviously El Paso's down here around an average of 9 inches a year, and then you start going up to 20, 28 once you're above 30, by the time you get to Austin, and then you're above 50 when you get to Houston. Now these red and these red lines, this is one standard deviation. So I have between 70 and 88 years of data here. So one standard deviation above normal, we classify that as a wet, and one standard deviation above normal, below, is dry. So what does this look like? And then I just did want to mention this as kind of follow up on the talk earlier, is that what's interesting is even though we know that the precipitation regimes are quite different across the state, in the 40s and 50s, you see the drought shows up in all of Texas. And likewise, in the 70s through the early 90s, when we were in the last positive PDO, you see that those dry years have kind of disappeared in some cases, like over here. And that's because really the difference between drought and wet periods is that there's fewer wet years and more dry years. And then you can see what's going on in the recent drought. So what does this leave us with? This is just the summary statistics. I want to point out that here for Amarillo, we've got a return interval about every 9 years for a wet year. I got 5 minutes? Okay, I've been rambling. 7, okay. So the point here is that Austin has the most frequency of dry and wet, so you can probably get by with about 5 years of data to look at. If you get to El Paso, you need about 10 years of data if you want to capture the variability. Okay, so then just UER, the point here is that if you can capture water in smaller watersheds, you're going to get more water from urban runoff, okay? So by the time you get into regional systems, the amount of water you can actually capture of urban enhanced, meaning that runoff from a pervious area that you didn't get before, actually becomes lower than if you can capture. So the idea here is that smaller detention, farther up in the watershed, and more of it will give you more water. Site suitability, begin with the end in mind, okay? You need to kind of have an idea first of how much available water, then that's going to drive, well, how much water do I need to get in the ground and what are the characteristics? You need to take a look at and do the site characterization work to look at all these issues, and then in the end, evaluate that as well as what the economic costs are. And don't let that happen to you. All of these are fatal flaws. What? Okay. All right. So this is a 2020 study that we worked on with Intera and Neil Deeds and HDR. And if you want to take a first look at this, this is a very handy document to look at. The grid size here is quite large, but this tells you everything that's in dark green and light green on this side of Texas. You could probably do some surface MAR. The dark blue and the light blue, you can probably do ASR. And obviously, Texas is doing a lot of ASR already. And you're pretty much limited to the Ogallala, the coastal plains, and the Hueco Boson Mesilla over here, as well as the Seymour for decent recharge opportunities. One thing I failed to mention is that BEG and Bridget Scanlon spent some time and they looked at what could you do with dry wells in Houston. And there's certainly an opportunity all along the coastal plain to be using dry wells. You're not going to get basins there, but you need some type of recharge enhancement method. So I'm going to go real quickly through case study, and Lynn will be talking about this in the afternoon. The phase 2, we've gone through a phase 1 initial screening. Basically, this is where we decide where do I want to spend expensive money to actually characterize a site? So what we started out with was 20 sites, and this is the Seymour Aquifer here. And then we went and collected all the data. We did the precipitation analysis. We looked at all the watersheds that led to these sites. These sites were picked in a combination of primarily area as well as potential landowner agreements. And then we ran through a whole ranking system. And so the main characteristics were, are there any restrictive layers at the surface? What's the expected surface infiltration rate, depth to groundwater? What's the aquifer hydraulic conductivity? And then the whole thing about surface water yield. And we decided that what we really want is something that's going to give us more than 200 acre feet, because below that, it's money. It costs money to build this stuff. Precipitation ranges between 24 on the west and 28 inches. And so when you run it through all the analysis of these different things, what's quite interesting is that the volumes of water in the wet years, which in this case is about every 5 years, is very high, but on the average years, the yield is much lower. So you typically are going to get these kinds of yields, and then you'll pick up some good, quite a bit of water in a wet year, and then almost nothing during a dry year. So this is just a map of the soil permeabilities. Soil permeabilities are not great out there, but in the western side of the district, there's some opportunities there. This is depth to restrictive layer, same thing. Depth to groundwater. As you go farther west, the groundwater depth decreases. Of course, this is due somewhat to a cone of depression, right? But also the hydraulic properties are better, so you can pull more water out from that area. And then this is the aquifer permeability. So where does that leave us? This leaves us with a map at the end where, if it's in blue, this is a good site, high probability site. In yellows and pinks, these are not probably worth pursuing. And so we see there's a few sites. I think we ended up identifying 5 sites that should be looked at closer. And then even in the east, there was some sites that weren't very suitable. So basically, this is just the process, and you would do this as well, any type of hydrogeologic analysis if you were doing whatever you're looking at, and that's going to help you decide whether you can do basins, or you need to do recharge enhancement, or you need to do ASR. So in conclusion, there's a lot of different ways to get water in the ground, and they're driven by hydrogeologic suitability, the available water supplies, and that, of course, is the big question is, after we do all work, we have to actually come up with design that will capture the water. That's it.
We have about 3 minutes for questions. If anybody's got a question, if you come up to the microphone.
I'm not from the Panhandle, but my understanding is that there's a whole lot of initiatives up there now to get the playas back working again, and where the farmers had drained them and filled them up or whatever and farming them, that the playas do a lot of the recharge up there. Is that correct, or have y'all looked into that, or what's the situation?
Well, so Rolling Plains is a little bit farther east of the playa area, and the playas in general, they certainly are points of recharge, but you also have to take a look at the trade-off between evaporation and the amount of recharge. Some of the playas actually have very low permeability because of they're sitting in the center, and all the fine-grained sediments have accumulated there. So if you're going to use the playas, which I'm not saying you shouldn't, but if you're going, you'll probably need to do some type of recharge enhancement. Otherwise, you're going to lose as much water to evaporation as you are to getting it in the ground.
Are there any other questions? I have one.
Yes.
Was it a bad experience that led you to using what has been a very iterative process now with us? Or did you start out doing your recharge projects in a very iterative way?
It's both. You know, we had a pretty good idea of how to do things, but, you know, experience obviously is key. And we also had the good fortune for us, misfortune for others, to observe a few projects that had that nuclear cloud that just, you know, they went up in smoke. And I would say that the way you avoid a bad project is you bring the hydrogeologists in first. And every bad project that I've been in is typically the engineers started it, they said, this land's available, we're gonna buy it. We actually worked on a project where they had condemned the land, and the city condemned the land, and the landlord didn't want to sell it, and it was a dog. They ended up putting a sprinkler and evaporating it on that site. And they built a several $1 million pipeline to get to it. So let the hydrogeologists do their job first to tell you whether or not you can get water in the ground, and then bring in the engineers. That's my advice, to avoid getting nuked.
Okay, thank you.
All right.